continue our discussion of propagation effects in the waveguides. We dedicated much of the previous meeting to nonlinear index issues, and we saw that the index in a medium is not necessarily what we expect in the linear regime of operation. There is rather a change that scales with intensity. And we discussed few manifestations of this behavior. We saw how a pulse of light, if it is strong enough, will undergo SPM, cell phase modulation. We will not repeat exactly what that is. We covered that well enough. If we have more than one signal in the same waveguide, there are mutual coupling effects. The intensity of one waveform can also affect the index as seen by a second one. So the intensity of one waveform can also affect the phase that is accumulated by a second signal. We call that cross-phase modulation, or XPM. One more thing we touched on is four-wave mixing behavior. When we launch in two signals, suppose they are continuous waves even, with some frequency separation between them that we know by capital omega, and we more or less showed, or I told you, that in nonlinear propagation we may encounter the generation of sidebands, or these satellite tones with equal spacing of capital omega above and below the incident signals. And this happens even though we do not launch any contents at those two new frequencies. So this is obviously a nonlinear generation behavior. We call this phenomenon four-wave mixing. And one thing I did not tell you is just how much power is being generated at these sidebands, and we can complement this now. So the power of these four-wave mixing products at the new frequencies, we can call them P4 wave mixing. And I will assume that, for simplicity, that the two tones have the same power at the input. So I'll call this P and P, and they do not have to be the same, but for simplicity, let us assume that they are the same. So what we'll get is a mixing power that scales with the third power of P. It will undergo linear losses like any signal finds linear losses in the waveguide, and the magnitude will scale with gamma squared and L effective squared. You remember what these are. Gamma is the nonlinear coefficient. In the waveguide, it's simply N2 times K0 divided by the effective area. Now, this parameter combines between material attributes and our choice of frequency and the geometry of waveguide that we fabricated. And the effective length tells us just how the nonlinear behavior is decaying along the waveguide as our input fields become weaker and weaker. Again, we discussed that at length last time. I'll just remind you it is defined as this expression, and we also saw that for short reaches the effective length is practically the physical length, and for long reaches it approaches asymptotically a value of 1 over alpha. So all that has been said and done. We did not put this result explicitly on the board last week, but we can complement this now. And all our discussion of nonlinear index has been in the limitation or subject to the condition that chromatic dispersion was absent or negligible. So thus far, we have assumed that beta 2 chromatic dispersion is negligible or weak enough, but next we'll discuss a couple of situations at least when it is non-zero. And in many practical cases, this is the situation. So when it is non-zero, then we have to solve the nonlinear Schrödinger equation with full display and for this equation we have no analytic solution in a general case. Analytic solutions only exist for a very limited set of specific input conditions. One such condition that we discussed in qualitative terms at the end of the previous meeting, but I will return to it in more detail now, is called a soliton. A soliton is an input pulse with a very specific temporal form. So our input field magnitude at z equals 0 follows a temporal behavior of a hyperbolic secant with a width parameter tau. And it has a certain magnitude at the input. And the propagation of a pulse with these characteristics can become rather surprising. Because normally we would expect chromatic dispersion to distort the waveform as it goes along. We can expect the nonlinearity to distort the waveform as it goes along. We discussed the spectral broadening that we see due to SPM. And it is not very intuitive to expect the cancellation of these two terms, but this is what actually happens at certain situations. So let us suppose for a moment that alpha does not exist. So we have no losses. Can we truly have a system without losses? Of course not. But for the sake of discussion, let's assume this situation for at least for a while. If this is the case, then a soliton such as this may retain its temporal shape over all position z. In the following sense, I have to explain what I mean by that. If I take the power a magnitude squared, surprisingly, I will get the same temporal shape as that of the input. Everywhere. Of course, does this always happen? Well, no. This miracle occurs only if certain relations are being maintained. This surprising results requires the following conditions. The shape is maintained in this form if, well, we already gave one requirement that temporal shape at the input follows this peculiar hyperbolic secant function, but that's not enough. Very importantly, there is a strict relation between temporal width and input power of that pulse. So in addition, a specific relation is maintained between width, namely tau, and input power. And the relation is the following: gamma, nonlinear coefficient, multiplied by A0 magnitude squared, which is power, multiplied by duration squared, is equal dispersion coefficient at the absolute value. Again, you can verify it. It's a advisable habit to consider units when you see something like this, to check if this is a sane and consistent expression. So if this is inverse watt meters multiplied by watts gives us inverse length here. So this now is second square over length, which is exactly the units of beta 2. So this is a consistent relation. One last thing before I stop for questions, and this is not enough. Beta 2 must be negative. Dispersion can be a positive or negative coefficient. It tells you if the velocity of the red is faster than the blue or the other way around. Both situations can happen, but the soliton is a valid solution only if the beta 2 coefficient is a negative one. It so happens. Yes, questions?
These terms are coming from the solution of this equation?
This is the terms are the coefficients of the equation. Okay, beta 2, gamma are the coefficients of the equations, and I'm guessing a solution of that form. And it turns out, if I were now to substitute this in and take the derivatives and whatever is necessary, if this is maintained, the equation is satisfied. You can test it. The nonlinear Schrödinger equation here is satisfied by this input form, provided that the relation between width and power is satisfied as well. So this looks like a miracle, because at least in theory, I can launch a waveform such as this to an endlessly long waveguide, and it will maintain its form, it will not distort, it will not spread. Wonderful. And for a while in optical communication, these sorts of pulses were considered very seriously, as the way to transmit information. Again, this is not a telecom course, but I'm giving a telecom course in parallel, and there is another one next semester dedicated to more advanced situations, and we very quickly realized that telecom is limited by nonlinearities. And this seems like a wonderful way to overcome nonlinearities. I mean, not just overcome, but even use them to take out dispersion. So everyone is winning on all fronts, except for two little things. So why we do not see solitons in optical communications, we do not. And one reason has to do with the name solitons. Solitons, this is a general wave behavior that was, it was first observed in waves in water canals in England in the 19th century. It's not something specific to optics. They are, well, the word means solitary waves. They must be separated in time from one another. They do not really like company. If I launch a soliton like this, okay, this is a time axis, and I'm operating a communication system, then after a while, maybe I want to send another bit of information, so I should launch another one. So there will be another soliton with some separation here. Unfortunately, soliton plus a soliton is no longer a soliton. We are in a nonlinear world, mind you, so a combination of two solitons no longer solves the equation.
Even if they are really far away from each other?
Exactly. If they are very, very far away, maybe they can forgive us. But they have to be very far away. Combination of two solitons, very strictly speaking, because this is a nonlinear situation, is no longer a valid solution. I mean, a valid solution is a very abstract and clean mathematical statement, but what this would mean in reality, that these two pulses will be distorted like crazy. And the only way to transmit a number of solitons like this is to separate them well beyond their individual durations. And this is a bit of an issue, because in a telecommunication systems, we have to launch as many bits as possible, and these spacings are not very convenient. But suppose that we, in some cases, might want to live with that. Then comes the other nasty issues, that we do have losses. Unfortunately, alpha is not zero. So suppose that I've adjusted power and width just right at the input. After a while, and a while can be a centimeter, a meter, or kilometer, depending on the material of choice, power is inevitably attenuated. So the relation between power and width is no longer holding. So after 1, 2, 3, 10 kilometers, this relation is no longer in place, and the soliton is no longer a solution, and it will gradually break up. So this is a perfectly retained shape in an ideal world that has no losses, but in any practical waveguide with losses, sooner or later this relation will fall apart. And I will not go into much detail now. People made a great many efforts to overcome this issue. Your first guess might be, okay, put in an amplifier, and this was attempted. Every 50 or 100 kilometers or so, you put in an amplifier, but this was not very successful because amplifiers change your power very drastically. In a fiber amplifier, for instance, over a span of 10 meters or 30 meters, you experience a 100-fold increase in power, and this was too drastic. This in itself was enough to disrupt soliton propagation, so point amplifiers like we are familiar with in communications are not a good way to do this. And then people came up with an even more clever way to amplify very gradually and smoothly as you go along. If, say, a fiber is losing 5% per kilometer of power, we'll come up with a very gentle amplifier that gives back the 5% per kilometer, and this can be done in a distributed continuous wave using a Raman scattering processes that I will address shortly. And in reality, you can make a fiber practically transparent. If you balance your amplifiers just right, it is possible to take out losses with good precision, so power is not lost and not gained, and the medium becomes in effect transparent. So you might expect that's going to be the end of it, but again, no, because what happens when you amplify something in nature?
Noise.
Exactly. Noise happens. Amplification is a process that comes from stimulated emission events in a medium, and Einstein showed us a century ago, even more, that stimulated emission goes hand in hand with spontaneous emission. You cannot, or if I translate these against sterile physical statements into the world of systems, you cannot amplify anything without junk. If we amplify the signal, then no way around it, we've added noise. And I will now can write another famous soliton equations, almost as famous as this one. And it says the following simple thing: soliton plus noise is not a soliton. So if we try to amplify these waveforms, even very gently, to take out losses, so on average we have not taken out power at all, then yes, we may be able to retain this relation at the cost of noise. And this noise will accumulate, and in the end of the day or in the end of the line will break the soliton apart. This can survive over hundreds and even thousands of kilometers of fiber, but sooner or later the balance will be broken. And after very intense research efforts in the 90s, people concluded that solitons are just too difficult to handle and too difficult to preserve, to be bothered with, and they are not used in actual telecommunication, even though in research and in waveguides and for all sorts of physics, this is still a very interesting playground to explore, and people continue to publish very exciting research about solitons, even though for the practical engineering purposes, they were proven to be just too delicate. Okay, so this was one interesting case to visit where we consider the entire nonlinear Schrödinger equation with nonlinear index and dispersion and losses. The last aspect I would like to point out to you here, that if we do consider dispersion, then the efficiency of four-wave mixing products is modified. Again, I'm not going to calculate this now. It is possible, but it's a tedious algebraic exercise that will take too much of our precious time. So I'll just give you the bottom line result. In the presence of dispersion, the efficiency of four-wave mixing processes is significantly reduced. We had a few minutes ago an expression on this board showing just how much power we can get in the four-wave mixing sidebands, and this was true for the case where we had no dispersion. If we do consider dispersion, we get something a little bit more complicated in the following way. It's going to be P to the power of 3, gamma power of 2, effective length. So this is what we had before, but there will be another factor like this. Losses coefficient squared divided by this term here. Beta 2 omega squared squared. There is something else here that I'll just skip for the sake of simplicity. So what we find here that if we have a larger chromatic dispersion, it takes the four-wave mixing efficiency down. What we also see, which is again to be expected, the larger the separation, capital omega, the more drastic the effect. So the effect of beta 2 becomes more significant with wider separation omega. This is to be expected. Why? Because chromatic dispersion expresses just how different is the propagation of spectral components. If I move further away in omega in a dispersive medium, then the differences in propagation between tau number 1 and 2 and 3 and 4 become more pronounced. So if we have more dispersion, or if we consider this dispersion over a wider range of frequencies, the efficiency drops. And again, you can find that if you want to substitute zero chromatic dispersions, we recover the previous expression. This is again a recommended simple exercise to take when you extend any sort of result. And you may plug in the numbers for any particular medium, losses and all, and see just when and how this becomes a significant correction. Is this a good thing? Is this a bad thing? Of course, this depends on what you try to do. There are no moral statements in physics. The same effect can be useful or detrimental. Again, from the perspective of telecom, this is a blessing, because nonlinear effects such as four-wave mixing are the biggest obstacle in optical communication links. We are launching channels 1 and 2 and 3 and 4, and we rely on separation between these channels to relay information, and we are making huge efforts to guarantee that there are no leaks, that information from channel 1 does not appear in channel 2 or 3 and 4, because if it does, it's impossible to separate them. But this is exactly what that four-wave mixing does. It is coupling power, this coupling signals from one omega to another omega, and this is a disaster. So any way to mitigate this effect, any way to reduce this effect is a fortunate break if you try to do communication. And this is why optical fibers, at least the best of them, deliberately maintain beta 2 that is not zero, because it greatly reduces the extent of four-wave mixing due to nonlinear index. But the same behavior, taking from a different perspective, it can be a problem. In many cases, you actually want to use four-wave mixing to do something. I will show examples later in the course when we discuss applications and communication experiments, but already I can tell you that four-wave mixing is a neat way to transfer information from one frequency to another. Suppose that this is my frequency axis, and this is a data channel at omega 1. And for any network reason, I want to transfer this information that is being carried here to a different channel, which is out here, omega 2, some difference to the right. Well, one thing you can do is add another dummy waveform, even continuous one, with no data or nothing, but just intense enough to the other side. And if this is strong enough and that guy is strong enough, four-wave mixing is now initiating between these two, and their product is landing out here. Actually, and out here as well. So if I play the game carefully enough, data can be carried over and converted from one carrier frequency to another. But to do this, you actually need efficient four-wave mixing. So, and if I say the same statement in the inverse perspective, efficient four-wave mixing processing that we like to do many times requires careful dispersion management. So we will make it our business to design the waveguide very carefully so that at least within that span of omegas, we have a very small chromatic dispersion. So beta 2 will be preferably close to zero. So yes, again, one man's noise is another man's signal, famous statement in action again. So this is a property of optics. It's not good or bad. It is useful or problematic depending on what you want to do. And again, this is just another example of what comes up if you take into consideration the entire view of the nonlinear Schrödinger equation. Again, what this has been more, again, due to the limited scope of the discussion, this has been more storytelling than any rigorous derivation of anything. But I am revisiting these issues very seriously in the next semester in the nonlinear optics class for graduate students. In the my student Yosef will give a class that I normally give for the final year of undergrad that addresses advanced issues of telecom, and there is a thorough discussion of this. So I'm not escaping the problem, I'm just delaying it to another time, but this is should be kept in mind in the context of our discussion. Why is that so? This is, again, a specific case of a general property of nonlinear optics. It's called phase matching. If you've taken nonlinear optics before, then you would know what I mean. If you did not, then probably you do not, which is fine. It is not required in the context of this discussion. But if you ever heard of, or if you know anything about phase matching in optical processes, it's the same story again. This is what gives this dependence on chromatic dispersion. Any questions on this? Okay, next on the agenda. And this next item is actually unfortunate period. In some cases, a noise is just a noise, or a problem is just a problem. And the next issue I want to introduce is two-photon absorption. So I told you already that losses in silicon proper are very low. So for example, at our wavelength, at 50-50 nanometer, alpha in bulk silicon at least is extremely weak. Silicon has excellent transparency as of itself. We already know that if we build a waveguide, we take additional penalties of roughness issues and bending losses. So, but even with roughness and bending losses, alpha in a waveguide can be below half a dB per centimeter. This gives an effective length that is close to 10 centimeters of propagation. It's quite good. Trouble begins when you crank up the power. If you have a transparent and long waveguide like this, it is tempting to use it for the sake of nonlinear propagations. So this is very useful for nonlinear propagation. Why? Because we have a long effective length, so we can build ourselves a waveguide like this and try to use it. And how do you use it? You launch great power inside. So we launch high power. But then we are in for disappointment, because the material and waveguide that were so nice and transparent before become opaque and they become strongly absorbing. We find that, unfortunately, losses scale with power. So not only we have those losses that we came to expect due to roughness and bending and whatever residual losses in the bulk, there is something else we express with the coefficient alpha t. The name t will be explained in a minute, times intensity. A little bit like the index. Just as we have index changes that go along with intensity, we also have losses changes that go along with intensity. And if we want to be very fundamental, this is inevitable. And I'm open brackets. This is not for test or anything. There is something in electromagnetism called the Kramers-Kronig relations. Have you heard about them? These are mathematical relations that connect between the real and imaginary parts of material susceptibility. And they come from a very basic fact that the world is that we live in a causal world. That if this would be in daily life, first I slap you and then it hurts, and not the other way around. Also, the same holds for matter, for electrons. You first put in the field and then it responds, and not the opposite. So if we accept that the matter in which light is propagating is a causal matter, then you can show mathematically that the real part and imaginary part of the response are linked. And real part of susceptibility, whatever, is what gives index eventually. Because if you recall, 1 plus chi is a directly constant, which is index 12, blah, blah, blah. And the imaginary part of the susceptibility is what would become later on losses. And in the linear regime, this is perfectly valid and possible for proof. But now we modify the rules of the game. So now chi is nonlinear. And if you recall, we have a first order term and a second order, and so on and so forth. So the index is no longer a linear index. The losses are no longer linear losses, but the relation remains. The world remains causal. So we still have limitations and restrictions, and we cannot allow complete freedom of index and losses. So even now, still, the way index changes and the way losses change are interrelated. If we have done something to our medium to change the index in nonlinear index, there must be manifestation in the losses. This is from causality. It's very basic. So, surprise, surprise, this comes out in a bad way. It's not fewer losses, it's larger losses. So this is the linear losses coefficient that we have come to expect. And this additive term represents now nonlinear losses. And this nonlinear losses behavior has a name. It came to be known as two-photons absorption. And I will explain in a minute. So nonlinear losses are due to two photons absorption events. Let me explain. Let us draw the Venn diagram of a semiconductor. Silicon is not direct band gap, I know, but for the sake of simplicity, let's do it that way. And we have a band gap here, which corresponds to, for the case of silicon, to a wavelength on the order of 1.06 microns. This is the energy band gap. If you express it as h-ni and transfer to ni to whichever wavelength, this is what you get. If we had a single photon, h-ni, where we are at 1550 nanometers, this means that the photon energy is considerably smaller than the band gap. And this is first and foremost why silicon is so transparent and this wavelength, because the energy of the photon is not enough to induce electronic transition. It is not enough. The energy is not enough to raise an electron from valence to conduction bands. But let's make another cartoon here. So same band gap as before. But what if I have two photons? One and another. So that even though h-ni is not enough to bridge the band gap, twice h-ni might be enough. So it's like saying h-ni is larger than half the band gap, if you like. So these two photons combined possess enough energy to raise an electron. the two photons together have enough energy for an electronic transition. Okay, but for this transition to happen, we must have two photons in the same place in the same time. So they can both interact with a given electron that is sitting here in the middle of the room and waiting to be elevated. So if we have few photons bouncing in the waveguide, what are the chances that two of them coincide in space and time? Very small. But the more photons we have, and gradually the chances of getting two of them here and now become more and more appreciable. And that's the essence. So the higher the intensity, then the larger is the chance for having two photons together like this. And in most cases, this is an unfortunate consequence, because if I try to use my waveguide for nonlinearities, for instance, the wavelength conversion that we had before, the way to do it is to send in more power. And the motivation to do it is exactly the transparency of the waveguide. It gives me a long effective length, so the process is efficient. But lo and behold, as soon as I try to take advantage of this and send in high power, then, oh no, all of a sudden it's not transparent anymore. And the effective length is becoming actually short, and the efficiency of the process is dropping accordingly. If I want to put this into equations, that, again, in terms of equations, the effective length approaches at the long waveguide limit, at least something like this, 1 over alpha 0 plus this extra term. So the higher the power, the shorter the waveguide becomes, effectively, at least for the purpose of and the sake of nonlinearities. With this in mind, we can define a nonlinear figure of merit in the following way, as gamma over alpha 2 photons. And this is a representation of how much nonlinearities we can squeeze out of a waveguide. It tells us just how efficient the nonlinearity might become. Of course, we want a large gamma because the efficiency scale with gamma, and we want to have long reach, so we want to keep nonlinear losses low. So the higher this ratio, the better off we are. Unfortunately, in silicon, it's pretty bad. We have an appreciable amount or appreciable extent of two-photon absorption in silicon, and we cannot crank up the power too high because it gets absorbed. And this means we cannot employ nonlinear processes very strongly. What can we do? No, more power doesn't help. More power just just gives in the smaller dimension also doesn't help, because this is intensity. It's watts per cross section.
Why we even want to send more power?
Suppose if I want to do wavelength conversion like this, like I showed before. So this is a nonlinear process. Nonlinear process scales with power to the third order. So you want to launch in more to make the process efficient, but you cannot. There's got to be a way around it, right? There's got to be a way to exactly. Here, if the band gap is, say, 1 micron, what if I use light at 2 microns? Then you cannot have two-photon absorption anymore. You might have 3-photon absorption, but again, now the chances are a little bit more favorable. It's more demanding to have 3 photons at the same place at the same time. So the best way around it, if we make H&E less than half the band gap, there is practically no, these are the acronyms, two-photon absorption, TPA. Only trouble is, in silicon, this will have to push us towards the middle infrared. Actually, you don't have to go quite that far because the efficiency of TPA is dropping as we begin to approach half of H&E. So at 1550, it's pretty nasty, but even if we start going to 1700 nanometers, 1800 nanometers, you start getting some kind of a break, but it still removes us from the telecom window of 1550 nanometers. And a big part of the appeal in silicon photonics is to work at that wavelength range, and here we run into trouble with nonlinear behaviors. What else can we do? If we have no choice, we may want to move from silicon to something else. So, as a last resort, in some cases involving nonlinear processing, we actually change composition. We could go to silica, for instance, but this will be a little bit too far out. Many times we switch from silicon to a material called silicon nitride. With proper processes, you can grow silicon nitride on silicon, you can convert silicon to silicon nitride, because it is still in a composition that is heavily based on silicon. And the big deal here is that the band gap corresponds to short visible wavelengths. So if the band gap is so large that at 1550 you do not see two-photon absorption, you do not even see 3 photons absorption. So silicon nitride has very low losses in the linear regime, pretty much like you would see in silicon. But even more than that, it has very, very weak two-photon absorption because the band gap is so large. To actually see nonlinear absorption in silicon nitride, you would need 4 photons together. While this is possible at the end of the line, it is much less likely. So you can safely raise the power in silicon nitride waveguides much beyond what you would do in normal silicon. Yes, please.
I guess there are many materials that have the same energy gap.
Yes, there are.
So why using this? Because it keeps the same.
Because it does not. Actually, the index here is on the order of 2, much lower than silicon. There are other options, like you said. The gallium nitride that we mentioned also has this property. This is why you make blue and violet, ultraviolet LEDs from gallium nitride, because it has such a large band gap. But if you want to integrate based on the silicon platform, the easiest place to turn is silicon nitride. It is more readily combined with silicon than most other alternatives. But yes, you can find a whole bunch of crystals and semiconductors that also have a very large band gap, but not all will be, I would say, silicon friendly. The silicon nitride, again, it's not trivial, but it is more readily combined together with silicon if necessary. Yes, please.
What's the penalty?
The penalty is that we are limited by power. Actually, when we hit of silicon nitride, the penalty is that you are no longer in silicon. That's the main penalty. Because again, very big part of the appeal was to use the same stack of layers, the same material platform that you have in electronics. And now we do not. So if we turn to this solution, then part of the chip, at least, or all of the chip, has to be something else, something that is not CMOS electronics, and it's a big penalty, at least conceptually. And when you do a lab demo, then maybe you do not mind all that much, but in the context of potential scaling and potential integration in a system, a big driver for silicon photonics is the word silicon, is living in the same realm where electronics exist. And now you're beginning to move away from that. Again, it's better off than to say gallium nitride, for instance, but it's a penalty, it's a considerable penalty. One last word here, just again to give some kind of encouragement. Every effect can be useful, even this one. Suppose that you do lithography, for instance, and you want to define a pattern on a piece of wafer. Let me erase some space here so I can explain. Again, this is hardly silicon photonics for the next 2 minutes, but when we do this survey of nonlinear effects, I must give some kind of positive character witness to two-photon absorption as well. So suppose that I have my wafer here, some piece of material, and I want to define a very small pattern. So what you do normally is focus a beam of light to a spot like this, and I would apply some kind of a photosensitive material called a photoresist, and it will react to the illumination and chemically modify at this region of illumination. So let's zoom in here. So as a function of position, we have some kind of intensity profile. No matter how hard I try, I cannot focus light beyond the diffraction limit that is established since the 19th century. So there's got to be some width here. So if my material responds to intensity, then the smallest attainable pattern is somehow restricted by a diffraction limit. This is why when you do photolithography in clean rooms with mask aligner or laser writers or whatnot, typically the features that you can define are hundreds of nanometers, give or take, sub-micron, maybe even a little more than 1 micron, because you're using light and you focus light at the diffraction limit, you get to the scale of the wavelength, give or take. If you want to go much lower, you go to electron beams. But what if now I have a different material that is modified not by absorption, but by two-photon absorption? What if now the photosensitive material actually responds via TPA? So single photons do not make any difference, and only when we have nonlinear absorption then the chemical changes in the material take place. So if I draw I here, now the response of a material like this would be something that looks like I squared. And this is much narrower, right? So in various fabrication protocols, actually two-photon absorption is quite useful, because you can take the same light source, which has the same diffraction limit, and use it to define smaller patterns, because we're using a resist material that responds via TPA and not due to single photons. In fact, maybe even not all the students from my lab know that, but the waveguide protocol that we have for writing in chalcogenide glasses is a TPA protocol. The works that we've been doing over these last few years, when we define waveguides by a direct laser beam, it's two-photon absorption. A tie-sapphire laser of 800 nanometers is perfectly transparent in the chalcogenide core layer. The only reason we see absorption and we see writing and lithography is TPA. So even this can be used for some kind of good purpose, but in the context of propagation of light in a waveguide, TPA is a detrimental effect. And unfortunately, it's the evil twin of nonlinear index. You cannot totally have one without the other. Questions? Okay, let's see how we're doing for time. Okay, we can tell a couple more stories. So far, the nonlinear behaviors I told you about all come from one physical origin, the electronic response. They originate from the way the electrons of the material respond to propagating light waves. And sometimes they respond in a nonlinear fashion, which gives us the TPA and nonlinear index. Let's erase this. As it turns out, not only atoms can respond to radiation in a nonlinear way, other entities might also do that, such as molecules. Suppose I have some kind of a primitive molecule, and I will draw it as a link between two atoms, and just like an electron is characterized by a set of discrete possible energies, so does a molecule. It can have a ground energy state and an excited energy state with some kind of energy separation which corresponds to some frequency. And when light comes and there is an incident on a molecule like this, two things can happen. It may find the molecule in the ground state with some probability, and then an incident photon can be absorbed, and a different one emitted at a lower frequency. And at the end of the day, the molecule will find itself in an excited state. So we absorb a photon and we give one back that has a lower energy. But the opposite might happen as well. If I repeat this cartoon here, and for some reason the electron, or the molecule, sorry, is initially at the elevated state, and now a photon is incident, it might be absorbed, and a different one will be emitted at a higher frequency. What this tells us is that light can be absorbed or generated or amplified in case there are very specific offsets in frequencies. Let me put this down in words. Certain optical fields may be absorbed or generated due to molecular energy levels depending now not on absolute frequencies but on difference between frequencies. So depending on difference between frequencies. Consider, for instance, this frequency that I called here Ni prime. If light at this frequency is present alone in a medium, and suppose it's below band gap, it will just go along with transparency and experience neither loss nor gain, pretty much experience nothing. But if I also send this second beam and maintain that the difference matches a molecular energy, then all of a sudden this light wave can be amplified. So again, you see, this is a very fundamentally a nonlinear picture, because the propagation of this light wave depends on circumstances. Again, in a linear regime, we have a frequency response which is absolute. The propagation of light at Ni prime is supposed to be presented in terms of a universal frequency response, which is requiring no favors. It does not depend on power. It does not depend on the neighbors. And this is what we expect in a linear picture of the world. And obviously this is collapsing because we have transparency without this guy, and we have gain if it does exist. So it's one of these cases where certain components may be amplified or not, depending on who else is around. And if we may find gain here, we can find, if this is now the longer frequency, it is loss. So both gain or loss can take place depending on frequency relation. These interactions between, just lose this, sorry. Let me get back. Do you hear me? Victor, do you hear me? This fell for a moment. Okay, good. So these sorts of interactions between light and molecular vibration, they have a name. They have a very special place in physics. They are called Raman Scattering. And they're named after the Indian physicist who actually was the first non-white individual to win a Nobel Prize in physics in the 30s. And now we consider this the way the world's supposed to be. But go back 80 or so years ago, or 80 plus years ago, it was not at all trivial, not all understood that someone who is not from Oxford or Cambridge can win a Nobel Prize. And actually Raman, if my knowledge is correct, was working in the post office and had a makeshift lab along his post office, post, to where he did this experiment that won him eventually the Nobel Prize. So he did many things which were quite amazing. And why do we care in the context of silicon photonics? Because of gain. As I illustrated to you, and again, I apologize, these are cartoons and not analysis. The analysis will come later in the year when we have the scope for it. The key word is gain. One of the main functions we need in any serious chip is amplification. Two reasons for this, very quickly. If we pick up losses over length, and sooner next week we'll have losses in couplers and losses in resonators and losses in filters. And if these accumulate, someone has to pay the bill. So if your device and system is large enough and complicated enough, sooner or later you'll need to compensate for losses. This is done over fiber with erbium doped amplifiers, and we need an equivalent on a chip, so we need gain. And if this is not a good enough reason, then in every system like this needs a light source, right? You cannot think of any optical system without a light source or laser light. And what is a laser if not gain with feedback? If we do not have gain, then of course it follows we do not have lasers. And well, you can argue, okay, what's the big deal? In semiconductors, we have lasers all the time, but not in silicon. semiconductor laser diodes happen in indium phosphide, they happen in gallium arsenide, and some more esoteric alloys if you go to longer wavelengths. And this is all for a very good reason, direct band gap. I may or may not have said something about it in the first week, but we'll not go into detail now. The minimum of silicon conduction band and the maximum of silicon valence band happen at very different K values, very different momentum values. The difference in momentum is just too big for a photon to bridge. And therefore, stimulated emissions or radiative transitions between bands in silicon are extremely inefficient. And if you have no stimulated emission, this means you have no gain and you have low laser, because the acronym is light amplification by stimulated emission radiation. There is a reason why this word is in there. So we are painfully lacking gain in silicon, at least from the electronic perspective. But we do have Raman scattering. So using this mechanism, we can introduce gain and even lasing, actually, to silicon. And we all like to say there is no silicon laser, but we have to be a little bit more careful. There is no silicon laser in the semiconductor sense of the term, because already in 2006, we had reports of a silicon Raman laser, which are very beautiful. This is a very heroic experiment. It has many complications that I will require next week to explain the entire scale of complications. I will get to it, but nevertheless, it is a silicon laser. What's the downside? I expect you to ask, what's the penalty? And of course, there is one. Part of the trick in semiconductor laser diodes is that you pump them with a current. Right? You have a device and you have a battery, and you pass current across a junction and you get light. Or in short, it is an electrically pumped laser. Pumping, which pumping is an initial condition, or it's a mandatory condition for any laser, is done by electronics, is done by current. What is the pumping here? Light. A Raman laser relies on optical pumping. So if you're a physicist, it's a fantastic achievement because we made a laser in silicon. If you're a system engineer, are you kidding me? I need laser 1 to get laser 2, so I might use laser 1 to begin with, and okay, what's the deal? Okay, so an optically pumped laser has all the appeal of the physics. It has only part, or small part, of the appeal in the system point of view, because if I already couple light in, so fine. I mean, let's use it. Why use it to make another laser in a different frequency and go through all the pain? And it's a good question, and it is perhaps why, at least I'm not aware of, any use of a silicon Raman laser in any device, in any system, in any data center. It remains in the part of the discussion of the papers and of the physics, brilliant physics. Again, you cannot yet fully appreciate the entire scale of complexity involved, but it could not cross over from research to systems because of the nasty fact that you need another laser to get the process going. Questions? Okay, nevertheless, I want you to know that this effect is available. And very briefly, one more note. What else can scatter light? Okay, so the way electrons oscillate can affect the way the optical waves propagate. The vibrations of molecules can affect the way fields propagate. One more thing is elastic waves. Again, this is a little bit awkward if you're not used to this concept, and I've become used to it over the last decade, so it's starting to be natural. In first year of undergrad, we teach you mechanics first semester and electromagnetism second semester, and we come to think of these two types of physics as being separate, which is of course not true. One way to convince you, what is an optical field? By definition, it states how much force works on a given charge. Force is field times charge, okay? And force is, force in the mechanical sense of the word. So again, this is very like hand-wavy kind of an argument, but if you send an optical field along some kind of trajectory, there will be forces acting on the medium, in mechanical forces. Well, let me draw a waveguide for you.
Like the photons momentum?
There's that as well, but this is an effect that happens mostly on boundaries. And what I'll tell you now briefly, and I'm not going to even begin to discuss it, but just tell you the story, is something that happens in a bulk. So it does not require that exactly. Suppose that this is my waveguide, and I will draw 2 copies of that waveguide. And in the one copy, I will solve the electromagnetic wave equation. And this will give me a mode. The fundamental mode looking something like this. And on the left-hand side of the same sketch, I will formulate another wave equations, the elastic wave equation. Again, I will not even begin to put it into writing, it doesn't matter. It's enough for the sake of the discussion to know that there is an elastic wave equation. It's pretty easy to believe. And the elastic wave equation has solutions. That's pretty easy to believe as well. Just take the electromagnetic wave equation, has solutions. So there is now a different solution, something crazy like this. So the optical wave and the mechanical waves do not really need favors from one another. I mean, they exist irrespective of each other, but they can be coupled because the propagation of electromagnetic waves exerts forces. If I have a numerical solution of this mode, I can actually calculate how the force map looks like. There are closed forms expressions to do this. And forces is exactly what is driving elastic waves, right? Just like if you want to make a pendulum oscillate, you will exert a force. If you want to drive this elastic mode into oscillations, you would need some kind of a force, and you can get this force from light. Again, depending on many circumstances that I will not describe, but at some carefully constructed cases, you can get that. So this will be stimulation of elastic waves. So I started with just sending light in, but maybe without even intending to do so, we found that we have excited elastic motion of the same structure. Now things become even more funny, because in nature there is an effect called photoelasticity. What does this mean? That if I deform a material physically, index changes. So the medium, this waveguide that I draw to you, at rest has a certain index, but if it is now starting to oscillate elastically, the index is oscillating. So when this elastic wave kicks into action, we have index perturbations. And this is because of photoelasticity. It happens in every medium. If I deform the medium enough, the index is not the same anymore. And now suppose that we have index changes in a waveguide. What happens to light? It is affected as well. So now in turn, we have modified the propagation of light. And this is if you're not familiar with it, it is tricky. I do not go into any equations or any quantitative description on purpose here, because this will be maybe too much to ask if this is a first glance of these behaviors. But just the take-home message is that light and elastic waves are not separate. Electromagnetism and mechanics are not separated. They are in fact related. Depending on circumstances, depending on intensity, might very well be, but they are related. If I send enough light, elastic waves will kick in. And once elastic waves happen, they get back at you. The propagation of light itself is not the same anymore. And I will stop for question in a minute. This conceptual feedback diagram that I showed you is known as Brillouin scattering. It's been predicted 100 years ago. It's been demonstrated in liquids 65 years or 55 years ago. It's known in fibers 40 years ago. And it's been totally absent in silicon. Why? I will finish this in a second, don't worry. Why was this mental picture broken? Because it turns out that in SOI, there are no modes like this. What we actually deal with is silicon and silica. And we have very large difference in optical indices between silicon and silica. This is why we can confine light here and it does not run away. Mechanically, it turns out that silica and silicon are very similar. So there is no elastic mode guided in the core. It is as if you try to build your optical waveguide with low index in the clad and high index outside. Light will never stay in a core like this. It does not agree. There is no guiding. So when you examine the SOI layer stack, we find the mechanical equivalent. We can support light in the core very easily. We cannot support sound in the core because it is not guided. It is running away down the silica. So why am I even telling you this? Because people found a way around it. Fabrication platforms or fabrication's capability have advanced to the point where you can actually suspend the whole thing. You can nowadays make silicon waveguides that are practically sitting in the air. They will be suspended on very thin pillars or connected with some hinges way down the end, but for the most of the optical path, they will be really free hanging. And now, the games begin. So when I started teaching this class, which is only 8 years ago, first time it was given, I used to say that Brillouin scattering is irrelevant to silicon, and this is how the entire community saw this, until some colleagues at IMEC Belgium and at Yale primarily have proven all of us wrong, have demonstrated otherwise. When you're taking out the underlying silica, then yes, very much so. You can get Brillouin scattering, you can get very interesting coupling behaviors between light and sounds, and just like the Raman case, we get gain. So we now have two mechanisms at our disposal to have gain in silicon, to have lasing in silicon. One is Raman, the other one is Brillouin. Again, this will be optical pumping, but there are very intriguing possibilities specifically around these sorts of physics. If time allows, towards the end of the course, I will revisit this in more detail. But even if I do not, then at least you are aware that this sort of physics is out there, and it is starting to be relevant and applied to the silicon material platform as well. Just to give one bit of information, there is a paper that is about to come out in a few weeks in Nature Photonics that is describing a Brillouin laser, not in silicon proper, in silicon nitride. The line width of these lasers is 0.7 hertz. think just how incredible this number is. We're talking about a frequency of 200 terahertz plus and minus 0.7. So this is like the 15th decimal point in frequency precision. This is insane. And on a chip like this. So that's Brilliant Laser for you. So things happen. This is very recent and very advanced. And again, I will get into it if time allows. And if not, at least we've given this limited introduction to the subject. Any questions? Yes, please.
You said that Raman scattering happens when we deform the material. But Raman scattering and even light absorption also changes deform the material.
Not physically. You're not seeing macroscopic scales being stretched and pulled. When we send an elastic wave like this, it has a wavelength, which is comparable to the light wavelengths. Again, there are fundamental reasons for this, but we speak of periodicities on the scale of a micron. So you can think of a chunk of silicon, 1 by 1 micron, doing this globally. And micron sounds small, but on the atomic consideration, it's a macroscopic chunk, a huge number of atoms doing this together. Raman happens at a single molecular level. It's one link between one silicon and another silicon doing this over angstroms. So the material as a whole, the 1 by 1 micron bulk, sees nothing.
So it has the same effect, but much smaller.
It is similar in the sense that light sees a different scenario. Light sees a different index. It is very different on the physical transverse scale of stuff. It's a nano occurrence and not a bulk material effect. Also frequencies matter because in the temporal frequencies omega of a sound wave, it's hypersound, but it's limited. 1 gigahertz, 5 gigahertz, 10 gigahertz at most. Raman scattering happens at terahertz, even tens of terahertz, because these tiny atoms oscillate at huge frequencies. So there is a factor of some 1,000 between those frequencies and the Raman frequencies. It's actually quite distinct physics. Anything else? Okay, so we have we meet again next Tuesday, so we meet regularly every Tuesday until semester ends, which is January 15th. This means we have 6 more meetings, not counting after this one. I will relate next week to one last nonlinear effect, which is very important for silicon technologies. It's called carrier absorption and carrier index. It just quantifies what happens when we introduce carriers. Index is changing, absorption is changing. It's quite useful and important. And after that, we'll start scaling up from the single waveguide to a device that has several waveguides that somehow interlink with each other. So happy Hanukkah, everyone, and enjoy.